Okay, it should be live. Let's wait for the audio. So I have audio feedback because this is important and this is something I don't see. Yep, audio is there. So we'll continue the project we started, I don't know, 4 weeks ago. And the idea here behind it is to create a cooking device based on a scale, so we can measure how much of what we are putting in case we need it, and a kettle which we can control the temperature and we can boil things and cook things with water, plenty of things. Last time we opened it and we looked around how to control it or how to interface it. Now we will do the actual interface, and I think I'll start with, so this one is pretty easy because here there is a relay which puts power or not on the kettle, so it warms up, and then there is a thermistor, so you can read the temperature. So really easy. I will not use the relay because with the relay you can not do dimming, and we want to dim the temperature. You have to use an SCR, but that's basic. We'll probably do it afterwards. What's more interesting is this, because I've never controlled a scale. So let's open it again. So there's still some batteries, so it should still work. Let's try on. It works. You have a lot of reflection, but here you see. Then if I press on it, it's a bit laggy, but it works. And how? Let's see if we press on. It's off. We already opened it. We'll open it again because we need to interface with it. And you have strain gauges here, and then some resistors which are changing with the strain gauges, and we need somehow to combine them to work correctly. Now, I worked with strain gauges, but not these kind of strain gauges. I worked with 4-wire strain gauges. Yeah, I think it's 4-wire strain gauges. These are only 3-wire strain gauges, but I think we can combine them to read. So let's open it and then we'll check it. Again. And the screws are not meant to be open and closed a lot of times. Oh, another thing which I found which we could use for the screws, if I find it again, it should be here. We can use these compartment boxes for storing stuff, and it could be the screws. Now you would want to write what's on it, so let's do that and write the content. Although here there are only 1 pair of screws. Yeah, I don't know if it's really that important. Let's just do it for proper measures and show how to do it. Up. That's scale bottom case. Well, that's a case. Okay. So, wow, it's pretty simple. So here, yeah, we have only 3 wires, and we can interface with this IC. It's a chip on board. It doesn't have any serial interface. This is what we looked for last time. So we will add some other things, some other sensors, which I have. I need to find my MISC sensor box. Let's put this out of the way for now. And in here, you see I have these strain gauges, but they have 4 wires and not 3 wires. And they need to be interfaced with something like, let's find one which is open. I'm sure I already used at least once. These ones. This is what you find very, very often as chip given with the strain gauges. These are load cell. Okay, load cell 4 times 50 kilograms. So up to 200 kilograms. It doesn't mean that you cannot put more. It's just that it means that it's not linear anymore. And most of the time you want something linear. So this chip, I think I still have a library for that, which I can interface. Oh, it's 1 and 2. So here, exactly, generally you have to put the two cells, A minus and A plus is one cell, B minus, B plus the other cell. We'll check how we can interface that. Let's try to find the data sheet for it. This is, maybe I still have the data sheet. Let me look in my data sheets, full screen. Okay, dev boards, plenty of things, MCU, sensor. Maybe I have it already in my new database. 7.1, yeah, breakout board. Here is no data sheet. This is the interface for my inventory. But we might find it here. Wait, Avia, this is the data sheet. Let's put the data sheet in the folder. Projects. I'm not showing all my projects because I want to have some surprises for you for later on. So I'll not show you that, but part DB, public, attachments, HX, breakout board, and if I copy the data sheet here in this folder and do the search again, here we see we can find it, we can look for the data sheet. So the data sheet, here you see, this is a load cell with 4 wires, 1, 2, actually only 3 wires. Oh, it also worked with only 3 wires? Maybe there's some different configurations. 1, 2, 3, and ground. So we need to find ground. Why am I thinking about 4 wires? Is this the only thing? This is A plus I minus. So you can do 2 times 4. Okay, maybe we have to combine 2 of them. What's E plus and E minus then? Which is on the breakout board. If we look, let me zoom on the breakout board so you know what I mean. Oh, okay, cannot focus anymore if it's too zoom. Here we have E plus, E minus, A minus, A plus, B minus, B plus. What are E plus and E minus? And also, they are controlled through a MOSFET. Here we have ground, VCC, DT, and SCK clock, and this is data. So this is a half duplex SPI. Or maybe it's not half duplex, you just read all the time. Then you cannot configure it. I don't remember, I've implemented it, but it's a while ago. Data out, yeah, from MCU, so it's only reading all the time. But what is E plus and E minus? Don't see E plus and E minus in this sheet. What do they mean with that? Here's A, B. I'm sure it's not the clock. The clock should already be on the board. Here we have again we have this transistor, so it's probably a copy paste of, so the reference design is probably reused. So E, you control the base, and then this controls here E plus and E minus. Okay, this is the connection to the 4 leads. Then we have S minus and S plus. And they go to negative A, positive A. Okay, so the E goes to AVD, that's plus. This is to control when to power on, and the minus goes to ground. So in this diagram right here, this is very probably V plus. Yeah, we see it also. VDD, so we have 5 volts going in, then we have the transistor switching on and off, and the E minus is ground. Okay, and then we have A plus and A minus. And now I need to figure out how to interface when you have only 3 wires, but we've seen a library. Strain gauge, 2 cells, 3 wires. Let's try Arduino because then we'll find plenty of tutorials. Load cell, strain gauge, gauges 3. This is the amplifier, load cell, 2 of them. This is not perfect. R1, R2, strain gauge, so only quarter bridge. We probably don't use quarter bridge. We have even more than that. This 3 wire. It's a quarter bridge. Okay, that's weird. Maybe there are some other interfacing measuring 3 wire. And we have 4 of them, so preferably we would just be able. I hate. Come on, Arduino CC, 41 scripts. You have 41 scripts going on. For sure, for displaying something, and without the 41s you cannot display. Who builds this? Wheatstone bridge, exactly. We want to build a Wheatstone bridge, and this is the resistor, which is variable, but there's only 1 of them. Seems weird. We've seen a thing previously, so this is not good, and yeah, we see the quality of. Probably there's the information, I just want to find it quickly, and I don't want to read a lot of things. Up, don't care. Let's look for images. If someone does, yeah, strain gauges, I also have these ones. We want something like this, and we want multiple of them. I've seen a diagram. Where we put multiple of them at the same time. That's a scale. Maybe there's something in here. Yeah, I'm thinking of something like that, where you put, so we have 3 wires, so 1, 2 could be 1, 2, 3, and then we need to pull the other one there, but I need to be sure, and I'm sure somebody already did it. Here, this looks like something promising. And another example. Here, 4 wires, you have 2 of them. Here we see the Wheatstone even. Wow. Here we see them. This is how they glue it. Okay. But let's have a look at a video where nobody talks. Can't you do a screencast? No. Here, this is probably how we want to build it exactly. So how does it work? E plus is the plus. It's getting only in this one, in the red. And what are the, so this is one side, then the minus goes probably here, and then this goes not to E minus, but to A plus. Is there not another diagram? Maybe we can combine both diagrams and understand how it works. Here we have the load cells, and I think that these 2 are from the same, are the 3 wires, 1, 2, 3 from one cell, and these 1, 2, 3 from the other cell, but I may be completely wrong. We'll find with this picture. So if we go with plus, let's get this one plus, and it only goes to 1. So I'm wrong already, because this plus only goes to 1 here. There are 2 of them. Ah, okay, then it uses the 2 here. So the 2 resistors are within 1 load cell probably. Then we have, let's take this one, goes, but we have no wire which is directly going out. So it's not this configuration, it's another configuration. How does this work? I would like to understand, because here it goes, so the middle one goes to this one, and then there are 2 resistors again. I think these are 2 resistors. And then it goes to A minus, and A minus could be this one, but here we have 2 resistors and not just 1. And the other goes to A plus through another resistor. So I don't understand how this is represented here. So I need to figure this out. I'll try. We can actually measure it, how this works, if these are 2 resistors and if they increase or decrease. Let's try that. Do we want to cut? But afterwards I won't be able to plug, and this is calibrated, but I have something else which is calibrated. So yeah, let's cut them and let's try to measure the resistance and see if it works. I think it doesn't change enough that I would be able to measure it, but we'll check it. We can still mark it in case we need to replug it. Where is here? This is this corner. This is this corner. Three here on this corner, and 3 here on this corner. You can actually see how it does the interface, probably. Maybe we can see how they connected, because they made it the right way. 2, 3. We need to remove the cell. Can do it like this, one side. That just should be enough. What is holding? The button. Damn it. Move the other cell up. Okay, so do we see how they are connected? Not really. Because of these white trays. Why do they have white cell screen on there? This is one process more. Why do they put it? Then we cannot read where the traces are going. Let's probe it. So, are these connected? We've seen in the... let's check. Bench. I have my remote. Better not remote. The bench. We've seen that we... here it's also written S plus and S minus. And here we have F plus. Oh, E plus. Okay, so they have the same names. So they might be connected. This is E minus, this is S plus, this is E plus, and this is E minus. Maybe we just need to copy what they did. But we need to figure out what is connected to what. So, are they somehow interconnected? Yep. These 2 black ones are interconnected. And I'm sure if I probe with other ones, we might find also other connections. Yep. Okay, so this is probably not connected to anything. So everything which is S minus, everything which is a signal is probably not connected. But here there's no writing. This might be connected with something else. Well, this one. This is connected to this one. This is connected to... maybe I was wrong. No, it's connected to this one. And then these two are connected together. Okay, so we just have to do the same thing as they did. I still don't completely understand how it works, though. But it does work. But we have to, and then we can interface it here, and we even don't have to use A and B, we only have to use one port. I thought we have to combine two and put it in one port and the two other on the other port and then add it. Maybe there's also this possibility to split it across two ports and be more precise, but here they don't do it. Probably we also don't need to do it. I'll still like to understand what the topology is, because I think, yeah, the two resistors, one is increasing and the other is decreasing. So how do they connect it? Let's try it out. On solder? No, not on solder, because I want to keep the colors. Actually, what I could do, maybe it puts strain, it's keep this, solder the wires to my connection, and then I can either power you through this or through this. I don't know if it changes. What if I put A plus here? Does it power this back on? Good question, right? And here, how do you control it? Because here there's only one output, so you have to control it by this one. If I don't power this one and only power this one, because if I power this one, it automatically puts some power here, I think. I have no way to control what it does. I only have data output. Or is the clock controlling the data? Let's have a look at the data sheets. Up. Full screen. Let's see. Base, regulator. Here there's no... you can control the rate. The rate is probably fixed to something where we have which gain? How do you set the gain? The oscillator is probably on the board. Let me check. There's no oscillator on the board. So the oscillator is not mandatory. Here is the gain. How do you control the gain? Here you have the rates, base, sub. Let's check the pins. Power supply, power regulator output, NC when not used. Okay, analog, regulator control, analog inputs. No, don't know what it does. Analog ground, reference bypass, channel positive, power down, cellular output. NC when not used. Okay, so you don't have to use it. Not connected when not used. And here we have the control. We probably have a frequency of 10 Hertz. So because we have a clock input, this is probably also controlling. We have an input. What it could do is just have an output clock and an output data, and we just have to grab. Oh, but we don't synchronize. Okay, so this is still in MOSI. How do we control what the gain is? I've implemented it already once. I shouldn't be, but it's years ago. Serial interface. Retrieve. Here. Pin are used for retrieval input selection. So if it's A or B, gate control and power down domains. Okay. Number of pulses. Okay. And the gain. Here's the table. You just control how many pulses, and then you see the data. how does it know from beginning on? Ah, next conversion. Okay. If you put 26 pulses and then wait some time, which is T1. T1 falling edge, this is minimum 1 microseconds. Okay, after the, and then T4, what is the maximum? T4, that's weird. Ah, the out. Who controls the out? Current next data output. Do I control the out and then I tell the D outs, and the D out is an input? No. The out can be an input, an output. How does this work? Serial data output. So I'm not controlling the output. Ah, okay. I have to wait. Next data output. I control that, and it remains high until the next process. When? How do you trigger the next one? Ah, okay. Now I get it. It says the out goes low when it is ready. Then, so it has a measurement. Afterwards, you clock the 24 bits. So you have the measurement, 24 bits measurement, and depending on, then it remains high. And after you clock that many bits, you just have to wait until it goes low again. And then you can pulse. Okay, so you always have to read that. I don't remember why I implemented it. I have to look in my archive. I have it. Let me check. I'm sure I already implemented it. And else we probably can find a library, which an Arduino library, which does it. I'm not interested in that. Project. Maybe it's even in my one of my. It's in my git. Git.qvoodoo.info. Explore. I did it with an STM32. That's this repository, and no, it's not in there. Thermocycler. Do you remember? Ah, I remember this. There's so many projects. Not this. No, 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 no. No, I've never pushed it because I never completed the project. So it's somewhere in my archive, somewhere else. Done. To do. No, I won't show you my archives of projects, but let me find the files. Archive, project. Just takes time. 111, 711, what is it? 711. 711. Okay. It's not possible that I didn't do it. Project's done. Okay, so it is in my done projects. I just didn't see it done. Yep. Oh, it's 3 years ago, almost exactly 3 years ago, 4 years ago, I implemented it. That's a long time. This is why I don't remember how it works. Library, I probably implemented it as library. Okay, you crashed. Projects done. Okay, now I can show you that here. Yeah, 2019. This is the last time I touched it. You see it from the date also. Did I implement it as a library? Very probably. Sensor. No. I didn't implement it as library. Let's check the application. Application.c. 2018. So it was maybe even earlier, 2019, maybe when I last copied it. No, I'm not using a library. Here are the ports. I'm not even doing the ports this way. I'm doing it another way. So it's super old. Now I have just B6 and B10. Exponential moving average. What? What is this? Channel conversion average. Why average? We don't care about this. Command versions. No. Bootloader. These are normal commands. This is not like this. Here. Setup. Set power delivery high to power down. What? PD is power delivery? What the hell? Clock. When I put the clock down, they call power delivery. Is it how they call it? Let's have it here. Pin. Yeah, power delivery. Power down control and not power delivery. I think I was confusing it with USB-C. This is probably when I started USB-C. So when you set it low, it powers down. And then you have to wait until it powers down. Okay. Here probably, am I using SPI or am I doing something else? Doesn't seem that I'm using SPI. Am I clocking it myself because of the number of pulses, and the SPI only wants a multiple of 8? That's very possible. I'm not using SPI. Get the conversion value. Yep, you see here 24, read all bits. And then I'm setting up and I'm set, so then I get it. So you see the clock high. This is what you see here. Clock high. You wait a tiny bit, then you can read the inputs, and then I store it in the 24 bits. Pad for 20. Okay, I'm not sure why I'm padding it. And then I pulse it low again and I wait. Conversion, and then I EM alpha. I have no idea what this is for. Calculate new average. Average minus plus channel A. This is a moving average with an alpha exponentiation. Why do I divide it by 128? That I don't know. And then I add the new average. Okay, I get this. I don't know why this. Where do I here? Request next conversion. And here, if I request channel A, okay, this is I'm trying to figure out which next conversion I'm using. Oh, conversion 64. I'm doing 64 conversions, and here I'm checking which channel, and then depending on the channel I set a bit, and I'm not changing the resolution. So I'm only using 25 or 26 bits. Here we have 20. This is 24 bits. Okay, this is 25 bits. This is 25th. Ah, here's a channel. Okay, 1, 2, 3. Okay, now I get it. 1, 2, or 3. And then there's only one channel where I can select. This is what we've seen here. Ah, now I get it. Channel 1 has this gain, channel 2 has fixed, so they have fixed gain. So channel 1 has always a fixed gain of 128, channel 2 has a fixed gain of, not a fixed gain, has a gain either of 32 or 64. So it might be a good idea to actually put the connections on channel A and B. This allows us to have the different gains. That might be a good idea. So we can put both things. So I still don't understand how the bridge works, but I at least understand that now. So let's figure out how the bridge works, how these strain gauges work. See, I'm also learning. Let's go back to the bench. We've seen somehow how it works. Now I'd like to try it myself. I didn't want to cut. I wanted to verify if I can do it in parallel, because then I could keep this as reference. I could simulate the button press for on and tar, which gives me a visual feedback until I have my own implementation. And this way I can correlate somehow if it's good or not. We'll keep it this with 3 volts. Yeah, we'll do it with 3.3 volts. I hope this module can do 3.3 volts. Datasheets says 2.6 to 5.5. So yeah, it can do. Selectable. So 10 samples per second or 80 samples per second. Why the one channel A can be programmed with a gain of 128 or 64? So channel A can also be programmed. How does it? Let me switch to the screen. No, not the screen. Yeah, you see everything not working, everything crashing. Let's put this here actually. Let's put the data sheet right there, so we can always have a look at the data sheet. So channel 1 can have 2 outputs and channel P has a fixed gain of 32. Okay, so there's a typo somewhere. Here you see channel A is here 128 or 64 and channel 2 is 32. And if you see here, you see that channel A 128 or normally 64, and here they say channel B. So I'm not sure which one is correct. In this diagram they don't, they show channel B, but it's probably here. This is the number of pulses. This is what's correct. Yeah, you see channel A 128 is 25 pulses and 64, but we'll also connect it to channel B. This way we can measure both, and we have this bridge and we won't require it for anything else. This allows us to, if it's really heavy, if it's more than 1 kilogram, probably the scale is only meant for 1 kilogram or 5 kilograms, I don't know, then we can still have less precision, but we can still measure the weight. And I'm sure that the strain gauges there work. So we got figured this out. Now we know how we talk the protocol. I don't know why I'm doing 32 bits and why I'm doing the moving average. How is it figured out if it's, so let's figure something out, is if it's it's 10 or 88 samples per second. Why would you want less? Is one more precise than the other? Let's full screen. This is my code, which we'll probably reuse because it works. Let's try to figure out where it's described. The sample rate, analog inputs, okay. Power supply and clock source. Ah, there we have it. Oh no, the rate fixes it. Okay, rate, which is an input. We have the rate here as input, okay. And on this module, which pin is the rate? Pin 15. Pin 15 is connected to ground through a decoupling capacitor, but the decoupling capacitor for something else. No, it's not connected to ground. Oh, I got it wrong. It's not connected to ground. Let's probe it. Let's just be sure. Yeah, pin 15 is connected to ground. So the rate is connected to ground like they do it here. It probably means that it is 80 samples per second, which is a lot. So we have here. Oh, no, it's 10 samples per second. Ground is only 10 samples per second. Why would they want only 10 samples per second? Yeah, accurate data rates. We don't need accurate data rate, so we don't need a crystal. Output format. Oh, 80 samples. Here there's a typo again. This should be rate. Ah, now I know why I'm doing the 32-bit conversion, the weird one, because the data is in 2 bits complement format. So, yep, this is the minimum. You have the last bit set. This is the maximum, and this is why I'm doing the 32-bit conversion, which is here in this code. You see it here. If the last bit is set, it is signed. And if it's signed, then I need to add to pad, because this means that this is a negative number. Oh, it makes sense. I get the conversion. So I did something good. And I need to fix this. This is not power delivery, it's power down. Maybe they use power delivery somewhere else, but here it's power down. Serial input. Do they say something with power down? Okay, that I get. Why is this module not using 80 samples per second? Because the more samples you have, no, although it's not too important, the better average you can do. You could do, okay, it doesn't make a lot. You can measure faster. If you're still measuring it once during 1 second, yeah, okay, it depends on the amount of average. So, but why don't they per default? Yeah, it is connected to ground. Why don't per default don't they allow 80 samples per second? If you can do more, you can do less. Maybe the data rate is too high then. If you have 80 samples per second, then the clock is too high, and small microcontrollers can't read it. That's possible. This is what they mean here. Using clock or crystal inaccurate. Ah, no, wasn't using external clock. Output data is directly proportional to clock frequency. No, it's not clear why you would use one and not the other one. Reset and power down. Here we have power down. Ah, this is what I'm controlling here. And this is why we see the 60 microseconds, which I've documented. Here, wait at least 60 microseconds to power down. This is what we have here. Then it's in power down mode. So I did do a correct implementation. Yeah, I think it does 10 samples per second. Here you see also the rate is connected to ground. Why do we want 10 samples per second and not 80? Because even with 80, you have 24 bits per second. That's not a lot of bits you can get per second. So 80 times 24, you can still read it fast enough. Why would you only want 10 samples per second? Let's find out. There must be an explanation somewhere. SPS, samples per second. 10 samples per second, 80. Even if it's for the rate, I mean, 80 times 24 bits per second, that's completely doable also for a simple microcontroller. Why would you want only the nominal output data when using internal isolator is 10 samples per second or 80 samples per second? When using crystal, the internal isolator is automatically powered down. Okay, we don't use that. We do control somehow the data rate because we are, so it only powers down and we read it afterwards. One conversion period. So why would you make the rate slower? That I don't get. Let's try to figure out if the internet has something. HX711 80 SPS. SparkOne has good tutorials normally. Simple but good. So here they also know. Here they pull it up. Why do they pull it up? VCC, VDD. So you have two different ones. Red, black, yellow. Documents. That's the data sheet. Getting started with load cell. Hookup guide. That's good. Okay, here we have 4 wires, but we don't have supported reading introduction. That we get, that I get at some points. Amplifier, yeah, it has an internal amplifier. This, yeah, so this is why I don't get why we use 4 of them. Because I think the 3 wires here, they put 2 of them on one bridge. They should, no, all 4 of them are on one. Combinator basics, okay, so they are talking about combinator. And here they do putting the reference E minus upper left. So they're also discussing about it. We'll have a reading, but why would you only want this advertisement? It's so hard. Suggested readings. Can I remove that? It's so painful. No, it's built in the text. It's section tutorial. No, it's built in the text. It's horrible. Pair type load cell, S type. Here, simple strain gauges, load cells. Oh, the wires need to be at the same length. They can be placed as equal distance with respect to each other underneath the platform. So it's important that the wires are the same length? No, I don't think so. So they are writing a Wheatstone configuration is built with a 4-button type cell. This is what we have the 4. Combinator board, using the combinator board, yeah. Here, exciton minus plus, so this is, and then we have the output strain gauge. We have 4 of them, but why can we put what is in the load cell? Here, there we have it. This is because we have a constant value. I get it now. This explains a tiny bit more, and we will measure it actually. Relatively constant. Between white and red, we have 880 ohm, and then we have a changing. This allows us to actually put it 2 of them and not 4 of them? Width and bridge, do all in the width and bridge? Here there's only one which is not fixed, but maybe this needs to be relatively similar to this. I don't completely get it. Let's try to measure it. Let's see if this is kind of accurate. So we go back to the bench and we will measure it. Do I have load? Actually, maybe I have load cells so I can understand. Maybe it's the same thing. Could have 3 or 4 wires. Okay, they have 3 wires. Some of them have 3 wires. Now, would it you? Yeah, this has 3 wires, so you can have these. We can use this load cell as an example. Can you use only 2 then, or just 1? Or do you always have to use 4? I would have to read more about the widths and bridges. Let's check it out. So here we have the widths and bridge. You are reading the DMM. Let's go to resistance. The resistance logo is not showing correctly, or the DMM is just broken. I think the DMM is just broken. Yep, it doesn't read values from the DMM. I have no idea why. Something crashed. Okay, now it should work if I put it to volts. Does it output volts? And I pulled a wire I shouldn't have pulled. Why is it not working? No, it's not working. They should be switched. Normally, if I press, they should reset. Does it work? No, it's not resetting. My script should be resetting the things, but it doesn't, and it doesn't read. Let's reset. Oh, it says can't establish link. Sorry, I'm debugging. Why are you stopping reading the measurements from the multimeter? You get the first ones and then you stop. What is wrong with my script? Connecting. Okay, connection established. There's something wrong with SIGROC. Why? Okay, I'm using the wrong script, sorry. Now it works. This is why it was not updating. Okay. So, and now it's broken. It does get the first measurement, but after that it stops. Seriously? Yeah, it stops. Something is buggy. I don't know what is buggy in my script, and sometimes it works, sometimes it doesn't work, and I have no idea why. Now it's stable. I don't know. I don't get it. So can I cheat and use multiple wires, or do you have to connect these directly to them? Do they have to be the same length? No, they don't need to be the same length because we're only measuring the resistance. There might be a bit of change in resistance, but we don't need to. So here it says that between red and white, it should be around 880. Red and white. Let's take that. This is red. I should have some white cable. Yeah, white crocodile. Let's have. It's not white. This one is white. White. Okay, then we put red here, and the white will put it on black. Where is the black probe? Here. So it's not 880, but 1 kilo. It's almost exactly 1 kilo. That's super precise. And if I change the cell, it should stay. It changes a tiny bit, but it does change though. And yeah, this is in one direction. I press here, it increases. I press the other side, it decreases. So it's not. This one is not fixed. Red and white. No, it's not fixed. Let's try. So white is in the middle. No, red is in the middle. Red is in the middle. So it's not white, which we want, but black. Here we have 1 kilo ohm again. What if I press here? This changes. I press here, it increases. Press on the other way, it decreases. But we have two which are around 1 kilo ohm. So it's not fixed. Yeah, clearly. White wire. And it's a fixed setup, so the leads shouldn't matter. This is why it's nice to have a multimeter with high precision, or with high digit count. This is 22,000 digits, yeah. Oh, damn it. So I don't. Oh, this is disconnected. We'll try it again to really figure it out. Yeah, this decreases. If I press it this way, it decreases. If I press it this way, it increases. So there are two which are changing. How much can I change? Around 10. And this way, around 10 too. So I can change 10 ohm, 1 ohm on each side. Let's try the other way around. And we can check if they're changed by measuring the two, but we'll see that. On this I can change 89. This I change almost 20. And yet, so this I change more. Now we will check the two. So white and red. So white and black. Sorry, white and black. They are in series. At least this works. Yeah, and they're in series. Okay, in series works and it's relatively constant. It's not completely true. Okay, why? So let me reread again how strain gauges work. Screen. Let's put a pause. I need to do something. I'll be back in 2 minutes. Full screen. Okay, I'm back. And maybe now I get why we only need, why we can either chain 4 up, because here the Wheatstone bridge says this only R2 are variable. So if we collect all 4 of them into R2, then it works. So originally electrical, an unknown electrical resistance by balancing 2 legs of a bridge circuit. Extremely accurate measurements. What is VG? That's the voltage. Why? What is between? Why are they connected together? Oh, this is where it measures. Okay. You need to measure between the 2 of them. And so if you know this, you can figure out this one precisely. Oh. Rx is fixed and yet unknown. Okay, I didn't get it. This is what we want to find. Operation. Okay, we want to figure out this one. Known resistance. Okay, known resistance is pretty hard because we've seen that the other one are, they're not really fixed. I'll try, let's try another cell, I don't know. Maybe it's because they are not really fixed. Balanced. No current flows. Ah, okay. Okay, so you adjust this one, so there is a 0 here. If the direction of current indicates whether battery is too low. Detecting zero current can be done extremely high precision. Okay. Therefore, if R1, R2, and R3 are known to high precision. But how, if this is variable, how do you know it? Then R3 can be measured with high precision. Alternatively, R2 is not adjustable. Across. Okay. Derivation, I don't care about the derivation. Okay, now I got that you have to balance R1, R2, R3 until it's 0, and this is why we have also assigned variable, assigned output measurement, because you want this to be 0, and when pressure is applied, then it changes. But which one of them? So they need to be matched, but we've seen that they are not fixed. Or with the multimeter, maybe this is some imprecision error. One is definitely more triggerable than the other. How do they do it here? Ah, here. Resistance wire. Okay, so this I get it now, because we want to measure this one. This is why we have the measurement between here and here. This is adjusted, so we know everything works out with the compared to the wire. Okay, but this is only one of them. Why, when you are using a combinator, do you need more of them and not just one? How can you combine 4 of them? We had the combinator somewhere here. Combinator basic. Ah, here. Full bridge strain gauge. This is what I got also. But they need to be matched completely. My understanding would be that one is, we can use 2. Let's use 2 multimeter and see what happens if we change with 2 multimeters. Is one increasing while the other one is decreasing? This is what I expect. What I expect is that in the load cell you have one side this and the other side this. This is what I expected, but apparently that's not how it's done. There is only one resistor and the other one is just a precision resistor. We'll check it. Screen, no, bench. Okay. So let's have a second multimeter. I'll show you the measurements in big. We're going to resistance. This is not a high precision. I think it's only 6,000 counts. Maybe it won't be enough, but at least we can see what happens to the one while the other happens. So let's measure across. You will go across red and black. Up, and you will go. I could actually put the value. Nah, I won't do it. This is Bluetooth controlled, and I have a script which changes the Bluetooth, which shows you the Bluetooth values. But I'm too lazy to fire it up, and it's not integrated in my streaming capabilities yet, because I never had the use for it. And so we will use white on one multimeter. Just this one, we see already 1 kilo ohm, and we will use red on the other one. I don't have a second red, so let's put black on it. Black to green. Okay, this one says also 1 kilo ohm. Now, if I take it and move it, it doesn't change anything. If I press, let's press this way. Here it decreases and the other is not is not precise enough. And here the constant value is between red and black. This is what they are claiming. No, they said red and white, right? Load cell. Where did they say it? That one here. White and red, that says this one is relatively constant. If I press here, and here it's not between red and white. The other one is constant. Maybe this one doesn't have enough precisions. We don't have enough digits. This has 22, this has only 6,000. Do I have something which has more than 6,000? Here. We've seen one digit changing. Whew. So if I press here, this increases. And on the other one, we see nothing. It increases here also. It increases. Nah, it's maybe just measurements. Yeah, this is not. Yeah, I need another high precision multimeter. Here, but it decreased the same way. Okay, so they are not counterbalancing. If I press here, you see it decreases by one digit, and it also decreases on the value on the multimeter, the the values you're using. Both are decreasing. So this is not what I thought counterbalancing, but both are decreasing. Well, it would make sense. I have no idea what they're doing. Now, you can only decrease if you would put it on the other side, so it makes sense that both are increasing. So there's really one which is a bit stronger than the other one. What is in here? Why do they put 2 for load sensor? Okay, there is a set color standards. The hacked home sale can have different for comparing the picture. Sorry, I'm reading the screen again. Reading that strain gauge load cell. So this is easy to find the center tab. And we don't care which one goes to plus and which one goes to minus. There's one which changes a tiny bit more than the other. 2 resistors. Okay. Now it says the combinator ball hood up the 4 load cell in such a way that 2 resistors in the Wheatstone bridge configuration are constant values and the other 2 are variable. Okay, but there are more than just 2. We could just apply and then do the measurements, but I want to figure out how it works. The data sheet and this one. This also has a diagram here with the load cell, with the measurements. This is where we see the measurement between A and minus. This is how, why. But where do we put the 4? We have 8, or we have 16 resistance. How do we connect the 16 resistance so it forms this bridge? This is what I would like to figure out. Load cell 3 wire bridge. No, not Arduino Stack Exchange, please not. Bathroom scale. That's Stack Exchange could be fine. This is how they do it. Why do they do it this way? The strain gauge elements come with a positively stressed sensitive portion and a negatively stressed sensitive portion. Do they? without an extra resistor. Ah. Okay, so this is how they combine it. So we have exciter plus here. Then we have the two variable ones, to minus, two constant one to plus, two variable to, this is to ground, this is to the other one. So we have R1 and Rx, which are variable, and the other one are kind of fixed. If I get it, if this is what I get, white, yeah, they're connected this way. White, black. Yeah, they claim basically two diagonal opposite sides of a width are formed by a positive strained element. Negative. Okay, negative means probably they changed it the same way. So I'm not sure what negative means because it didn't decrease while the other one increased. They both decreased. We can even check it. Let's check again with the multimeter if that's the case, to be sure with the one which is precise. Bench. Okay, so this one we remove it because this one is not precise enough. This is, I also don't recommend this multimeter. I expected something else. Let's only use this one and check if it works. The red is the tap wire. Which one is positively strain gauge, negatively? I hold it always this way. Now we have between white and black. If I press, it decreases. If I press the other side, it increases. Okay, if I press, it decreases. Now, if I measure between red and black, and if I press and it decreases, they both decrease with, yeah, it also decreases, so I'm not sure, it decreases less. So here we have 10, 1 ohm. Yeah, we have 1 ohm difference when I press, and here you have 15 ohm, 1.5 ohm difference. So one is more sensitive than the other, that's for sure, but they both go to the same direction. Yeah. So I don't know what they mean with positive strain gauge and negative. With compression all 4 positive strain, the active resistance are reduced and it pulls the parts one way. And on tension increases, the full bit goes the other way. Why are all 4 in a big rig with a maximum? Okay, so they combine the resistance. Now I get it. No, almost. Good schematic. Here. They do. Okay. Let's look down. Here. This is what I mean, positive and negative strain. Why does positive and negative? So we have one of these load cells. What does this mean? Diagram like this. Not too correct. Here they don't say that negative means that when you press it increases while the other one decreases, but let's see. Does not match occurring in the other picture. I have no, they say that when you press some, it should off-balance the other, but this is not what we've seen. If managed well, the reduction of resistance in the negative strain portion will offset the increase of resistance in a positive strain portion. But this is not what's happening. The total white black should be constant. This is not what we are seeing. Because if I have white black, we have 2, and if I press, it should actually be both, so it should be even, see, 30. So that's not what's happening. That's definitely not what's happening. Maybe this strain gauge is kaput, but we can still check with the other one. But and you see, if I press here, they both release by something like 20, 25, which makes sense. Yeah, 20, 20, yeah, because both of them are added. So let's try with another one to see if we just have a defective strain gauge, which I don't believe, but I mean, it can still be possible. It's just for my understanding, because the description we are reading doesn't match what we are measuring. So this gauge goes away. This comes here. Okay, here we have the same. If I press, does it remain constant? No, it doesn't. It behaves like the other one. If I press, we have around 25, 20 difference. Oh. 2 ohm difference. 20 digits. So let's try here, center tab, and see if it behaves the same way. If when I press, it decreases, and let's try the other one. If I press and it decreases, then there's something I don't completely understand, or it doesn't match. Yeah, no. Yeah, it press, it decrease. So there's not a positive and a negative one, not at least on the one I have. And I'm sure it's not just a bug for mine. So I don't completely, but we can still use it even if I don't understand it. Full screen, let's continue. One still needs to set up the full bridge so that the voltage divider moves in opposite direction with added load and the 4 difference. Okay, so that makes sense, but we'll keep it as it is. So what I want to do is that when this decreases, when this one increases, which increases the different balance. And these should be constant, although G1, yeah, this is G1, this is one of them, this is the other, this is the third one, this is the fourth one, and this is a signal. This is why S plus, so E means exciter plus, exciter minus, because there's plus voltage and minus, and then we have signal plus, signal minus. This is why S plus and S minus. Now everything makes sense. So I get this, but I don't get why this works with the thing I mean, red, black. We'll just use it as it is. Yeah, we'll just use it as it is. So let's go back to the data sheet. We'll do we put it in A, or do we want to put it in A and B? I'm sure this is 2 times the gain. We have to check if it bottoms up, bottoms down with this, then we can still put it to B. For now, let's connect it to A. And do we care about the resistance? No, but we should have some kind of same resistance. We will use this with, don't I have already one? I'm sure I already used the strain gauge, because I wrote a library. Where is the strain gauge I used? Did I? Wheatstone sensor? I have plenty of them, but I'm sure I soldered wires on one, and it could be nice to reuse it. Let's see in my parts bin. Remotes. now you can see what I'm doing. So, no lightning detector. This not used, that's not soldered. Where did I use it? Where I had to remove it? Oh, I had to leave it in. That I don't get. No. What is this? Oh, that's something in gyroscope light. Huh. I have enough of them, but I'm surprised that I don't have one where the things are soldered. Ah, here we have another one with 4 wires. One of the strain gauges. This is probably the one I used. I thought so. And here we have a module which is done, which has just one of these resistors. But this one I've never used yet. This is probably what's... Ah, and this is the resistor you need to change to match until it's 0. This is R2 and this is RX. This is why it's a trim pot. Now I understand how this works, that they've read it. Okay, so we'll just solder one. We first want to do with soldering. Afterwards, do we want to put it on a breadboard or do we want to connect the wires directly? Wires directly for now is fine. Yep. Breadboard, you can put it still the other way around, but then we don't see the things. Yeah, the wires are fine for now. And do I still want to use... So let's switch on the soldering iron. This makes nice noise. Up. Let's solder the wires. And then we can reuse the code I have. We just need a microcontroller and flash it if it's still flashing. We will check this out. I'm sure it's a blue pill what I used. So this I need to heat up, so we put it straight. Up. Okay. Let's do the same for the other one. And now I get that why there is a resistor, a trim pot, which you can change on one and not on the other, because you know the values and they are matched. And here putting it in this direction allows you not to have to change resist, but yeah, it always needs to calibrate. Okay, we will solder DuPont wires directly to these connections. Oh, the other one is done. Okay, so this is done. We will put jumper wires directly. We will solder them. So let's get some jumper wires. Oh, I had a bag of jumper wires to cut, ready cut jumper wires. I don't have any more. But we can make them. Plenty of female to female. We need one which is only 4. This is the most required ones. I never have here 4. We could... Oh, this one I don't want to cut because it's nice on the other end. I think the one which I cut all gone. I want them to have kind of the same, from the same bunch, because this way they are the same length and they have kind of the same resistance, because we will increase a difference in resistance to 128, and we don't want to bottom up the scale too fast, else we have less precision. 2, there are 5 here. Let's use these ones up. There'll be a remaining cable. Up. I will cut that. Round in the middle. Up. Strip the wires. As I hope. Sometimes you get DuPont cables which you cannot solder. I'm not sure if it's because there's aluminium inside, but or some kind of other metal, but you can't solder on them. This is really weird. Oh, I cut it. Damn it. I need another box where I put DuPont cables which are ready to solder. 1, 2, 3. What's plus and minus in the signal is probably not that important. Yeah, because we will have plus or minus. Well, what we still didn't figure out is why do we want only 10 samples per second? Once we soldered and once we got the values, we will try to figure this out. So, exciter minus, we will put this to black. And it's nice that they put the labels on it. Exciter minus, this will be black. Okay, then we have S plus, this will be white. Although plus and minus it's not important for now. I should have done the other way around. Let's do it the other way around. Oh, damn it. How much can this scale measure to? I don't remember. Probably 5 kilograms, maybe 10 kilograms. I don't know. So let's put the cables also this direction. Okay, then we have S plus. It's the white one. E plus, it's gray. Oh, E plus is not, okay. I need to remember that E plus is not what I think it is. But it's nice on the board that they have the writings on it. Okay, so this is E minus. That's S plus, so in this case will be A plus. And then we have E plus, this is the gray one. And S minus will be A minus. And we don't have to, that's good, we don't have to destroy the electronic scale. And now if we connect something here, it should work. So let's get a microcontroller and dev board. Up. I have a huge dev board box. This needs to be cleaned up, like a lot of things. Up. Look at it afterwards. Is it written on the scale how much it can now? And I've thrown away the box already. So we take a blue pill, because I'm sure I programmed it for a blue pill. First need to burn the bootloader. No, this one has already a bootloader, and the bootloader should be fine. So if I connect it to micro USB, yep, and then I try to compile this code, it might work. Let me check. Let me put another screen, and you can see what I'm doing. 1, 2, 3, 3, 3 is 3. Oh, I can do it this way. Screen, show you screen, increase the font, and stroller control -F. If I plug it in, it should appear as a serial device, and it does, and there's already a firmware on it. Not sure what firmware it is. Data project, it was in which folder was it? I think it's done, or to do, 1. Done, 2019, that's the firmware. Let's try to compile it. Rake, I changed a lot. This error, I know it. I need to change it in global.h. But will not use user input. Okay, this is fixed. Rake, this is not fixed. It's always the same error. It's hard to do something which is compiler friendly. GitHub master. I think that needs to be this way. That's for sure. Yeah, oh, I didn't even do it correctly in my source code. Okay. Bootloader. And just have to copy paste it. Let me fix that up. Bootloader.c. And oh, although it looks right. Okay. Why are you not compiling? X32, that's normal. Application +1. Oh, no, application is in Win32. External Win32. Ah, now okay. Now I get it. Up. This should fix it. Yeah, now it kind of fixes it. Let's get the other fix done. Application.c. This should be around. So this says the line 120, 246. 246. This is not possible. This is what you're complaining. Oh, there are plenty of things which I changed meanwhile. But for now, I just want to compile. Terminal. Strict overflow. Why? Terminal send. Assign signed overflow not occur when changing. What did I do wrong? This I don't remember. This strict overflow. Let's try lib. And I'll probably not. I'll not do this project with an ESP32 because there is. Why do I don't want to do that? I could do it with an ESP32. USB32 with STM32. Why wouldn't I do it with an STM32? Because you have to, I mean, too few. Do I need connection? Do I need Wi-Fi connection? No, I don't think so. I want to do everything offline. I could do it with an STM32. That's true. I could. Let's fix it for now. Cancel you. Up. You are. No, this is right. Lib terminal. I didn't decide it. I thought I would do it with an ESP32 because they're easy to get and they're cheap. But I could reuse that. LCD controller. I need an LCD controller. I have one for the STM32. I could. Here, terminal.c 316. 316. This one, terminal send void. Okay. 435. This is the end. Yeah. Where are you complaining about an overflow? Assuming overflow doesn't occur. Occur. Oh. I'll just did I fix it? Let's just copy the whole file from the other one. That should be fixed in the 4 years, but I don't see where the overflow happens in terminal 355. It's possible. Lib terminal row up. I copied from the fixed. Yeah, I fixed it. I already fixed it somewhere. This then rake flash. Now it should be flashing. Here we see we are going into the bootloader, and here we are seeing we are back. And if I connect to it, ACM0, someone else is already connecting to it. I have another thing which is connecting to it, but I don't want you to show you what it is. So let's switch back to the bench while I do that. Up this. Okay, now I can show you. Yep, now it works. Let's go back to screen, and here you can see the measurements. Channel A, channel B. Oh, and I can measure how many samples per second. Why? I did it correctly. Resistor. Why would I know the resistor? Why? How am I calculating this? Conversion. Where do I print? Where do I print my values in my code? I don't see it. Maybe it's another. Here. Okay, resistor. Double resistor channel average 22. I remember. Now I remember the project I was using. I was measuring the resistance of cables. Okay, so we don't care about the resistor value. But we want to plug it in. So let's disconnect that. Now it will try to connect all again. We will have a micro cable coming from here, micro USB. Do I have a port 3? Do I have a cable 3? I need both of them. Here's a cable. Up. Here's a port. Now if I connect it, you should up. Yep, it appears again. And now let's connect both of these. So I need 4. Here I have 4 wires. black is ground. Here we have ground. We power it with 3.3 volts, even if we could power it for 5 volts because this is 5 volt tolerant. But we'll do it with 3.3 volts. This is purple, 3.3 volts. And what were the pins? Let me look in my code. Application, we have power down and clock is B6 and output is B10. So clock is gray, this is B6, and the other one is B10. Where is B10? This is far away. Why did I put the two here? I don't know. And if we connect it, now we should see some measurements. And we see some measurements. And we are at 6 samples per second, 7 samples per second. Channel B makes no sense, that's completely normal, but channel A, that's what's important. Yeah, channel B is just garbage data, it's not connected. And we have 10 samples per second, around 10 samples per second. But for, I do all the measurements, don't I? Or am I only doing 128 and then channel B? Conversion, that's 2 complements. What am I doing the call? Only question shall after several conversions, which takes some time. This 88. We still don't know why we only have. I'm doing a lot of averaging. I'm doing every time 0. 64 samples. I'm averaging on 64 samples. And then I'm changing the channel. We can increase. Okay, I do stop increasing. There is an automatic game mode. If this value is too high, then I go one below. And else. Channel A is not channel B. Okay. And then, okay, I'm just changing between channel A and channel B. Channel A, yeah, my code is not bad. My code is actually good. So this value is quite constant now, and if I press on one of the scales, it should change. Yeah, it does change even a lot. Wow, this is quite good for my measurements, but it means I can use it. And what I just don't, I'm not allowed to do is excite it while the other is already excited. So I only allow one of both to be enabled, either this one or mine, which is fine. I can just disconnect mine and then do this. But this way I keep the one working in case, and we'll try what happens. Oh, I'm not trying what happens, but we can close it because we've soldered the wires. We are happy with that. So will this click and will this work? Let's disconnect this and let's try if the scale still works as a scale. 1, 2. Oh, why do you think? There's power now. I did press on a button, maybe without paying attention. Does this thing work? Yeah. Oh, no. These are the 3 screws. This is pressing. Okay, that I didn't expect. It's pressing a lot on the screen. It's probably not making a great connection. Let's try. Switch on. Yep. Yep. I'm pressing too much on my cables should be a bit thinner. The concept works, but implementation is not complete. Maybe if I screw 1, 2, 3, if I screw it, the pressure is high enough that I don't need to do my conversion. Let's try this out. Why do I have 3 screws? 1, 2, 3? Why not 4? Or is there a screw and I just lost one? 1. 2. 3. Now let's see if it works. Oh, now it works. Yeah, so I have an interface and I could calibrate with this calibration values. I'm not allowed to use both of them at the same time. Yep, this way. Right, fits inside, yeah. Although it wouldn't bother. Make a difference. This wire shouldn't go here. It should, damn it. This wire should be back here. Okay. Let's put this back in. Okay. We have the feed, so 0. That still works. Now, if I switched it off, so let's try what happens if I also excited. Are the measurement values completely different and it will put just some garbage? No, it actually works. What? That's weird. Doesn't mine also work? No, you see it's not stable. Ah, it is stable. Why is it working? This one is working, but mine is not working anymore. No, it is. It just takes time. So okay, both are working. This is weird. Yeah, maybe just one of them puts more plus than the other, or sinks a bit more current. That's completely possible, or just puts it higher. But we have both of them which are working in parallel. Okay. Why not? But it's not complete. It's not completely working. It has some issues. Let's figure it out. Now, this is 0, so 6. Let's wait until the measurements are stable. And the average is I'm averaging not fast enough. You see now it's stable, but it takes 8 seconds until I have a stable average. Now, what happens if I switch it off? This is switched off. Is the average the same? Will it be the same? Around 7.4547. No, it's not. So it does change the time. Oh, it decreases. No, here it's 5.54. So it's not completely the same, but maybe because the voltage is not the same. And I don't know. What we could also test what happens if we put something that change the weight. For example, if I switch on this, it's calibrated, I put this. If I unplug the power, yeah, it changes something. So it's not perfect. You can't use both. There's kind of small change. If I put it on, then it doesn't change it back. Oh, it does. It just took a bit of time. And if I touch the wires here, which makes sense because I'm changing a plus and minus, it also changes. See, when it up, it doesn't change a lot though, but it does change. No, maybe it's fine to put, no, it does change. You see the value changed again. So not both in parallel, but at least it doesn't break. And see, it changes by 20 grams. Max, it's written, okay, it's written 10 kilograms is the max. And yeah, so my code works. This, we can completely interface with it. That's one part which is completely solved. The other things we need to do is calibrate it. So when well, let's switch this off. And now if I press, does it increase or decrease? It does nothing. Come on, let's reset. Okay, it's reset. Let's let it settle. Now it's settled, and if I press on it, it's increasing. Okay. So it's not, this should be, if it would be ideal, this should be 0. It's not ideal, but it's good enough. And this should, now it should revert back to this value. And it does very slowly, but because it's not because of the measurements, it's because of how I'm doing the average. And you see it settles down to this value. And around, yeah, you need around 8 values. EM alpha, what is this? EM alpha is 8, yeah. You need around 8 values for it to settle. This is what we see here. But yeah, okay. We have an interface to the scale, which works nice. We can put the wires where we want them. I'll probably put it somewhere else, but for now we'll leave it here. We could actually put this thing somewhere inside here and then have the 4 wires to interface. This is probably what I'll do. I'll hide this either back on this board or back in here. Not sure if this is structural data. Then we have 90 degrees cables. This will be this way, 90-degree cables, and then we'll have 4 wires coming out of somewhere. The front, the back, I don't know. And that's how we will do that. We don't need this anymore. We can put this here, we can put this here. And why? This is the other way around. Up. Okay, we have our weight scale. Now, we just need to do the same for the load cells. Let's put the load cells back. I just need to do the same for the kettle, to control the kettle. I will need a calibration value. I need to calibrate the scale, that's for afterwards. For the calibrating, it's simple. Just put 0 and then you put something which you know is 10 kilogram. We know that this can measure up to 10 kilograms, so you can put the 10 kilograms there. This is, I didn't decide yet on what I want to do. So the scale is done. Let's remove the scale and let's go to the next one. We have the solution for the scale. I didn't decide if I want to do an STM32. Why not? Because I have everything, even the LCD driver, or an ESP32, which would give me connectivity. Maybe I want connectivity to monitor the food without having to connect over USB. That could be useful. You have a web interface to it. And it costs a lot less. than this, and it would be my opportunity to actually port my code to ESP. That's for another time, because these are expensive now. This. So we found how we control it. Let's open this box again. Up these wires go here. That's for later. Up. Let's open it again. And I think, oh, I hope I still have my writing. Up. Let's switch back to full screen. Bench. Did I throw it away? No, I have it. This one. Yep. I know what all the connections are on the bottom here to put the power. So we have the 4 feet. Let's get the box. Switch this off. Tack. I'll show you what's. Let's open this, and then we will talk about the options, and then I'll decide which one I'll use. And this needs some magnetizing. Maybe the screws are not magnetic. Huh. That's the wrong screwdriver. I was just too lazy to get the right one. That's the right screwdriver. No, the screws are magnetic. Okay. We'll put it with the feet. 1. Before we do that, okay, let's close the project. So I'll open this, and now I want to figure out why we wouldn't do 80 measurements per second, 80 samples per second. Why do we want a rate of only 10 samples per second? Let's try to find out who talks about it. Up. That I don't get. So we are full screen here. That was my code. And we started a search already. We probably don't have it anymore. Midstone, how do we know? That's not it, that's not it, that's not it. Okay, let's start again. HX711 80 samples per second. Rate. How do you change? Yeah, not how, but why would it put it to 10? That's my question. Why would you want to need 10? Moving average. That's also what I'm doing. I have plenty of samples. I had 128 samples. It takes 8 seconds, but I have 128 samples. Here, pulling high auto data sheet. ADC noise is worse. Okay. Makes kind of sense. Unless very quick setting is required, 10 samples per second. Okay, it's just because it's more stable. Does the datasheet say something about noise? Noise? Even they could at least say noise. Low noise, low noise. Yeah. Here. Output data rates. Okay. Rate VDD. Here we have. This is where it says it. Rate 0, we have 150 nanovolts of noise, and a rate VDD, this is up to 80 or 80, we have 90 nanovolts, and also Output settling time, yeah, that's normal. It's because it's ReadyD is faster. Input offset drifts, that's okay. Rate what also changes to rate. They put everything with 0. So let's keep it at 10 samples per second. I'm sure 10 samples per second is plenty sufficient for the cooking I'm doing. I'm not doing high-speed data. So we have this figured out. That's good. Let's switch back to, come on. Yeah, this button. Let's switch back to this view. So inside here, we have all the connections. We will reuse it. This board, let's show you again this board. If you don't remember the other one, and we still want to remove it. Yeah, we want to remove it. Up. 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 This is kettle PCB kettle case bottom. But okay, the screws are there. So we will not use this LCD. We will put our own LCD where we can have nice displays. Also it makes, okay, what we will keep though is these buttons, these lights, and this pot. But do I want to make my own PCB? Yeah, I'll probably make my own PCB. I'll just scan this. Is it more than 10 centimeters? Maybe we don't care about how many centimeters it is. Where do I have a ruler? This one doesn't belong here. This one belongs here. 15 centimeters, around, yeah, 15 centimeters. I'm not sure, does Chelsea PCB used to have the rule that everything under 10 centimeters is $2? Is it still this way? Or is it now with the board size, board area, and not with the longest size? I don't know. Because if I want to reuse this, I need to solder. I could solder on these points and hold this chip, not this one. This one is just the IC. Oh, there are markings on it. I could hold this chip. This is the microcontroller which handles everything. This is the LCD controller. I could reuse the LCD controller actually. Was it a nice LCD controller? Let's try it out. Switch on. Oh, it's super loud. I don't want to touch it while power is on. This is the buzzer. I could reuse all the connections, just remove the original microcontroller and tap on the connection, or just hold it on a reset. I just need to reset pin. Let's check. I think it's not a nice. No, I will have another. Let's have a look at it just to figure out how it looks like. Okay, this is the input. There, I shouldn't get any shock. Oh, actually, it's not that bad. What's on here? Come on, I know that. Let's unplug this. I'll explain you why I disappeared. Simply because the RCD triggered in my flat and it cut off the internet. Simply because I touched this, or one of these, this live with the case, and the case is grounded, and this made my RCD trigger. So no power, but I'm back. Yeah, I wanted to say that the screen is not half bad, but I'll probably want to change it to some. So let's have the screen display again, and this time we do it correctly. reusing the screen could be just fun because it's integrated. We could reuse the complete board. We wouldn't have to design our own board. We just have to change some other parameters. But so let me think if I want to change that. If I want to reuse it. Let me see if it's nice enough. Then we can reuse the complete, almost reuse the complete board. We'll come to that later. So let's switch on, and this time it should make poof. It should be just on. Yeah. Custom mute. It was start stop. Press for 3 seconds. 1, 2, 3. Is the button stuck? Yeah, the button is stuck. Damn it. That was why it wasn't putting well. Let's let the resistor bleed. Yep. Okay, so let's put it correctly. So we can press the button. Probably have to put this way around first. Let's zoom a tiny bit more up. Oh, this interface is horrible. That's the button, and that's the, there's a slot. Oh, it's indented. Okay, now I get it. Wait. So you need to, now it works. Okay, no, it's okay. So let's screw it and let's have a look. The problem is I want to display some menus. I want to display what I will cook and more information than just that. I could have an external display, or the question I'm asking now, will it be able to have, does it have enough characters for me to show text? Because if it has enough characters for me to show text to display what I will be doing, then it's good enough. We can reuse the character, and it's just, I mean, it's a lot easier to use a TFT and do and just display things, but it's not that fun. It would be fun to just disable that, reverse the segments, and then just display. There's probably a data sheet for that. VK1072C. Let's check. VK102C. 1072C. VK1072C. Is this a very known? Yeah, 8 times time 4 data sheet. We have a data sheet. It's downloading. I'll show you the data sheet. Full screen. That's the data sheet. Software configuration built in. Yeah, 5 volts. That's fine. And yep, that's the chip SOP8. We have the segments. The commands are probably very easy. Data, write, read, clock, chip select. It means that it's probably very similar to SPI, but we'll have a look. Write command. Okay, operation write mode data, mode command ID, and the mode ID here. Code mode. Okay, code command. That's write mode. And then command mode, data and command mode, command address and data. Then we have command or data, mode addressing. It's very similar to what I've already did with other chips. And we can actually use, this is very similar to SPI. Do we have the same amount of bits? Yep. No, not yet. Here's the start bits. Yeah, we can use SPIC 1, 2. This is just a 1, and then we always have, yep. Although can we 0, 1, 2, 3, 4, 5, 6, 7? This is bit 8. So we just need to configure so that the first clock has a 0 address in RAM. Then we have data. Oh, this is weird. This is weird. Then we have only 4 bits, so that's the commands. Then we have the data. Okay, it doesn't work completely with SPI. Here we have 8 bits to start, then we have all the time 4 bits. So this could work with SPI, maybe even with that, but this wouldn't be able to work with SPI with CS in the middle. Command code 100. We could do it this way though. And then command. This is weird. Why? What is command I? What are you doing here? Ah, this is to tell you can print lots of commands, but that's weird that you need to say this preamble. We can't use just SPI for that. Why do we have 2 command modes? Writes mode commands. This is display RAM address 1 display commands ID. We have 2 different IDs depending on what we want to do. But it would be fun to reuse the display. Now, yeah, we wanted to figure out, do we have enough segments to show, to display some things? So let's switch on. You cannot switch on without the kettle on it. Oh, you could. It just doesn't work. Why is this LED always on? Maybe you need to switch on with the kettle. Let's wait until it fades. Okay, at least it doesn't beep 2 times. Now it beeps. When you remove it, it beeps. Okay. Start cancel for 3 seconds. Let's try. 1, 2, 3. No. That doesn't work. Did I break? Okay. Now it works. So what's nice is that we have, I could reuse the symbols. Formula would be something, boil, yeah, 100 degrees. It's just water boil. That would be nice. Warm is heat up some other things. Formula would be for my special dishes. Is it always fixed 100 degree? And then we have the time. These are 7 segments. Let's go to warm. This is the different T's. We could reuse it. No, I'll just use a 7-segment display. 7-segment display. I'll just use an LCD display, which I'll put on here. Yeah, I have some. We'll do it this way. Oh, I know what I forgot to do. I need to set which IP I want. Down, this, you go down. Password. Okay, maybe internet will be cut off. Maybe doesn't seem so. No, it seems fine. It's using my Ethernet card and not my USB card. Yeah, so we'll not use the display. The display is nice, but we'll not use it. We'll just design our own PCB. Wow, we want to design. I mean, it could be nice, but I want to have plenty of menus with pictures and so on, so not the display and not just text. We will have a nice LCD, which we will put here. So let's do that. And now we can really talk about what we want to mod. We will redo the board. We will put our own encoder in, we will put our own buttons, we will put our own LCDs. So we will copy the boards, and what will make the huge difference is, let's unplug the power, and let me go back to this. Okay. to this view. And what I wanted also thought about doing is using a Raspberry Pi, which controls everything, something, or a single board computer, it could be anything, with a huge display. And then here, the problem is that this display uses too many of the pins, of the SPI pins. Actually, we don't need SPI pins. This, we know that the HX is not completely SPI. We could software program it. So one of the solution would be to have a single board computer where you have where it's easy to put a display. It's just a display, and you could easily update it and so on, and you could write the whole code in Python. That would be one solution. I don't, and I have plenty of single board computers, so why not use that? Because we will have lots of recipes, and maybe with the recipes I want something which is easier to use. Do the holes matter? This hole matters, this two, these two. Why do they have two holes here? Why do I have these two holes? Maybe for another model? Maybe this is what, no. I don't know. I have no idea what these two holes are used for. So we will, but what's nice also is here we have 5 volts already. We have an input power. What we won't use is this. This is a relay, but a contact relay. And we want to be able to change the temperature smoothly. And this wouldn't be able to last on and off. This is a relay, right? This is not a solid state relay. I don't think so. This is a mechanical relay. Let's check it out. Because if it's not a mechanical relay, but it's really a solid state relay, which would be nice, which I wouldn't have seen in such a case, then it would be nice. Else we need to find another solution. So BPDSS, let's check that. Screen here. BPDSS 106TM, 106TM. I'm 99% confident that this is a mechanical relay. I don't care. T conductivity, relay general purpose, SPST. Yep. Let's have a look at the datasheet. Oh, no datasheet. 10 pieces. Yeah. Heavy relay. Oh, come on. Oh, what's this website where you have to block a notification, say hello? Come on, is this internet? It's such a pain having to click all the time 1,000 things before you can access everything. If is nice. Let's have a look at the data sheets. Data sheets in English. This is... so how many switching does it support? Oh. Here. Maximal 30 operations per minute. Electric. This is T, right? There's no 0. Because if it's 300 per minute, that's a lot. That's 5 times a second. Can this be used for 5 times a second is quite enough what I want to do here. Yeah, that's a mechanical relay. Because then I don't have to change anything. I could reuse the board completely. I'll just have to put my own code on it. 30 operations per minute. That's every 2 seconds. That could be nice, actually. I didn't know that. And electrical 10 to the power of 5. Let me check how much it is. 10 power 5. That's not that much actually. Let's say we switch 10 times a minute. How many minutes would it last? How many hours would it last? It would last 136 hours. That's not a lot. 166 hours. If we change it that frequently, if we change it once a minute, it would last 1666 hours. That's a lot though. Maybe we can just reuse it. I didn't know that they would support that many operations. I would say 10,000. This is 10,000, 100,000. No, this is 100,000. A mechanical add rated resistive load, no load, and we probably have no load. So yeah, between 100,000 and 10 million times we could reuse it, because we have rated resistive load, true, but we won't use it for all the time to be that warm. Although yes, okay, so it's 10,000, 100,000 times we could use it. Yeah, we could almost reuse. We could almost just repurpose, reprogram this microcontroller. No, I don't want to reprogram a microcontroller. I want to program my own one. But we could completely reuse the board then. What we could do is first have the first prototype reusing the board, and if we want something better, we could create our own board. So what I wanted to do, yeah, this is a mechanical relay. You see it's our 100,000 operation. I thought it was a bit less. 100,000 operation, then it breaks. And I want to be able to control, to ramp up the temperature. Okay, no, I cannot use this. I want to be able to ramp up and down the temperature at good speed, because I want this to be quiet when it boils. And for that, I need to be able to control how much energy goes that. I don't want to hear the clicks, and this would not be good enough. I mean, it would not give me a good control. So there are several solutions to that. What you can use is a solid state relay instead of a mechanical relay. So it switches electrically only. And there are different kind of electrical relays, of solid state relays. The simplest one is something like this. Let's find me something else. Let me show you something else. Relays. I have lots of them. I have a box full of relays, but most of them are mechanical relays. Oh no, here we have mechanical relays. Oh, here we have high voltage relay. I think this can support, 100,000 volts, something like that. This is crazy. Here we have a tiny, that would be lovely to use one of these solid state relays. The problem is this only supports 2 amps. Here we have something like 10 amps. We have probably 3,000 watts. Oh no, yeah, 10 amps, 2200 watts. So this is 10 amps. This meager relay won't be able to hold it, because else I would love to use it. Do I have other relays which can support more? So what you could have is something like that. I think they're called SCR. I don't know what SCR stands for. Side control relay, let me check. SCR motor controller. Silicon controlled rectifier. Okay. This is an SCR, right? Or did I have the terms always wrong? No, this is an SCR, yeah. So what's inside here is almost like that. It is actually like that. It's just controlled differently. What you have in the SCR is a triac. This is the triac. And the triac allows you to pass current easily. And what you can do, I have things which are bent. Yeah. So what you can do is just how does it work? It switches off when it crosses 0, and then when you put there 3 pins, one pin is going. This is here. Here we have a pin in. Oh, this is out. So we have a pin here in, but it is also going to the middle one. Yeah, it's going to the middle one. We have a pin here in, then we have one out, and then the third one is a controller. And when you apply voltage to it, it allows AC to go through. When you remove pin, it doesn't immediately remove. The triac switches off when it crosses 0. It switches on as soon as you apply power, but it switches off only when you cross 0. How this works is this. Here you have a trim pot. This uses a resistor value, which then only puts on a. When you see the AC waveform is going up and down, and at some point when this is high enough, then it switches on. When it is long enough in the circuit, this is when the triac opens. This is why you have this resistor. It just allows you to set in which port of the half wave, at which point of the half wave you will enable it on. And this is how you dim things. And here you don't, this is probably also a triac inside here. And there is a zero crossing detector or circuit. What it allows you to do is you can only switch on and off at the 0 point, which is the cleanest actually. Because here, if you switch on and off at just any points, it's not a very clean AC waveform. So this has the advantage that you don't need to wait until it crosses 0, which it does 100 times per second. But then you just use a lot of load at any point in the voltage, which is it's doable, but it's not super clean. Here we have a zero crossing circuit. You see ZC, that's zero crossing, which tells you there are two things. The zero crossing circuit tells you whenever you cross 0. This is enabled. Then you have the PSM, the pulse sine modulation. I don't know, pulse signal modulation. This has an optocontroller which actually triggers this pin. So when you set it high, the optocontroller completely isolated from mains and then allows you to use it. Here we have a bridge rectifier because we need AC to operate the zero crossing circuit and the optocontrol. Although the optocontroller, no. Why do we have a... Maybe to operate the zero crossing circuit, there are two choices. Yeah. To operate the zero crossing circuit, you need to... It needs this bridge rectifier. But not only that, also to enable this pin. But is there some kind of regulator? Oh yeah, here we have a kind of a divider, a voltage divider, which goes also here. Oh yeah, so, okay. So it also controls the power on this side. Do I have, then, so ideally I would love to have this one because this has this does the zero crossing itself. So when you apply power, it will only enable or disable it at zero crossing. Here you have it to do it yourself almost, and it's not completely clean. And then you have these SCRs, which you probably have seen also. And they are in combination, but I don't know if they use the zero crossing. I have other ones. How many amps? These are 2 amps only. Do we have a zero crossing here? This one, solid state relay, and this is 5 amp. That's still not enough. I need 10 amps. Sad. This is direct, so this is DC. This is DC. And I think I have AC. Yeah, 25. Yeah, 25. This is the things you can find with AC. I think these also include zero crossing circuit. We could test it. This is also AC and 25 volts. 25 amps, plenty sufficient. But it's huge. I don't know if I want to have such a huge circuit outside. I mean, it's meant for 25 amps, so it can really control a lot of power. But I would love to have it something that which is as small as this one. This is up to, well, it's not written on it, 16 amp. I think the BTA 16. This is the really up. This is the triac, and this says that it goes up to 16 amp. But 16 amp is the maximum, and you have to cool it. You have the fan here. Here you have this. So I think this circuit is almost like that in here. And but I'll just use. So what I could do is use a dimmer. So I can really have fine control, but it doesn't look nice. But we have huge water mass, so I don't need a fine control. Using this, we have clean waveforms because we switch on only when it crosses 0, and I can still change it 100 times per second. That's good enough for me. So we will use one of these relays. Which one looks fake? This one looks fake. This one says made in Taiwan, so this one looks genuine. Here it says nothing, so it's probably not genuine. And the writing here is bad. But I'm sure it's if it's not genuine, always use at least twice the power rating. But it's as heavy. Can we open them actually to see what's inside? I don't think I've never opened one. But maybe everything is just on the blob. So we will use this directly, which we control using 3 to 5 volts. That's awesome. 3 to 5 volts. That's awesome also. Ideally, I would use this one because it's a lot smaller. You can put 4 of them, but this is only 5 amp. We need to control 10 amps. So we will just use this one. Or this one. This one looks also nice, and it has the connections. Oh, can we just, yeah, maybe we'll use this one. Yeah, I'll use this one because I don't need the wires. It's half as big. Also 25 amps. This looks also quite genuine. We will use this one because we can directly unplug AC from here. What we also need is power to power the whole board. So we probably don't need this one. Oh, N is directly connected. But then, okay, this is this one. This is directly going here, and then that's the outputs. And here is the PTC. Yeah, this would be nice because we have already a voltage grill, but I have bricks, which allows me to have 250 volts. Does this fit? No, I'll not use this one because the spades don't fit. If they would fit, I would have used it. So let's use this one and let's have wires. I'll probably not put my screen here because I need an external box to put this one in and to put the other things in, the buttons. So I will not reuse this. I'll have a complete separate board. That's possible. The controls here are nice though. Yeah, maybe I have just another board which has this and the power converter. The power converter which we will use is something like I should have some. Yeah, I have some. Oh, I have plenty of them actually. Something like this. This one gives 12 volts. It's not what I want to. I want 5 volts. can I see it from the side? Which one are 12 volt? Which one are 5 volts? Probably this is also 12 volts. Yeah, 12 volts. This is very probably 5 volts. We have plenty of them here also. 5 volts, 3 watts. Well, do I want to use 3 watts? No, I'll not use. Even with... no, I'll never use 3 watts. 3 watts at 5 volts. No, I could actually. Because if I use Wi-Fi, but even if I use Wi-Fi, I wouldn't use 3 watts. So we will have this, and this in a separate board, which provides power. Wow. What we could also have is one of these, but I think I use it because I want 12 volt and 5 volt at the same time. Yeah. Which I only want 5 volts currently. Yeah. So we will use one of this, one of this. This way we can control smoothly the power going to the kettle. This gives us power for everything, for our whole electronics. And we can put this somewhere isolated in a box. Oh yeah, and this is also just the same, almost the same thing. Here you have a trim pot, but here you actually have all the signals you want. You see SCR 0 crossing. No, this is SCR 0 crossing, 5 volt ground. The problem with this one is that this is not isolated. What you get here is actually connected to mains. There is no isolation transformer, it's just a capacitive. And this does the same thing that I explained with this board. Same principle built in here. You actually also see the components. Most of the components inside here. This is very probably the zero crossing circuit. You don't have an optocoupler because this is not isolated. And this is also why I put glue on all the points, because if you could touch it, it could be mains reference. And now all the metal pieces are not mains reference anymore. It's not meant for you to touching. It's you put on a panel and that's it. But yeah, that's the thing. So we will use this. We will use that, and we will have a board. And somehow these wires will not go directly here. This wire will go outside, and then we will have wires. Oh, we have to cut it. We will have to cut this cable, this mains, and this will be in the middle. And then we'll have just, can this be in the middle? It would be nice to have something, so this, but then along with it, we also need the power from here. So there will be a second plug going in here for this board. Then I need to make measurements to have these buttons. So I think I still want to have these buttons. We can, actually we can have this in here. We will still have a lot of space. This, is this high enough? Is there enough space for that? The problem is we still need to control that. So we'll have some wires. Can we put this also inside? That would be nice. If we could put this, so this is a heat sink, it's probably good enough. Can we put both of them inside? That would be really great. If we could, it's really tight. No, there's not enough space. Because then we just have to plug the how is it called? The scale. on the side using just a button, and we could have everything inside here. What we could do though is have a split board where the LCD just is on top of that and the LCD just sits here. No, it's still it's too high. That never fits. Just that doesn't fit anywhere. Let's unplug this. Yeah, that doesn't fit anywhere. That needs to go outside, and it needs to be somehow protected. So we will have two cables, one going in here, which we can directly connect here, and we could put mains. No, we can't, because when we control it, we want to have still mains separate. And we still need some wires to connect plus and minus here. So we'll have kind of a USB port. So we have plus minus, and then the control line. One would be enough actually. So 3 wires, plus minus, and the plus going here. We will have one power wire, and we will have one for 5 volts. Yeah, so all the AC is going here. This cable will be cut. There will be AC coming here, but this wouldn't go here again. This would go directly to the board, and then we have plenty of space for this board. And yeah, there's plenty of space. We would have the double-sided board. We don't need that much double-sided board. What would be awesome would be to have a scanner, but I don't have a scanner anymore. I have to redesign the board. And then we have the NTC connections. We will recreate all the buttons, all the LEDs, because they fit nice. We just take a picture of the front, then we have the LCD. The LCD I wanted to use, do I have it here? I should have it somewhere here. Let's see if it fits. This one. I want to use, maybe it's even too small. I could use bigger. This LCD, I could even use a tiny bit bigger, but this, I have plenty of these LCDs, at least. And this way it's 1.8 inch. That's probably enough to show the text and to show the status. There is 160 by 125, and I have lots of them, which I can just solder on the board and then display. And it's actually, there's a side, so no, it's good. It fits. We could have a bit more space on right left, but we will use this display. I still didn't decide if I want Wi-Fi or not, if I want an ESP or an STM. Maybe I don't know if I want remote control. If I don't want remote control, we could do with an STM. If I want remote control or remote monitoring, we could do ESP. ESP has also the advantage it has plenty of space for recipes. It's easy to flash. I could flash it over the air, and it's cheap currently. And I want to learn with it. We'll see, but we don't need a lot of inputs, outputs. We only, we do actually, 1, 2, 3 buttons. Then we have this, one output for that, and 3 outputs for the scale. So it's not that many outputs. With 20 outputs, we should be plenty sufficient. And 8 outputs for that, for the screen. 20 outputs should be sufficient. But now we know. We have this, we have the ACM which works. I didn't show how it works, but it's nothing complicated. Here we'll just use an ADC. An 8-bit ADC is plenty sufficient. We even have a 12-bit ADC, good enough. We'll redesign the board. This is the next thing I'll do. Take a picture, redesign the board. I'll make tests just with that to have everything working, but else it's fine. Well, that's, I won't continue. I won't do any coding or I won't do any design now. I just wanted to explain what the part we will use and how we will use it. And next time you'll probably see some progress. I also need, that's also what I want to do. Check how loud this gets when it gets warm and have a recording. But that's for another time. It's probably also even for another video. For now, we are done. So enjoy the rest of the weekend. And I'll keep you up to date once the kettle is built. Bye bye.